3. I have 3 90-degree interactions. Okay? So, 2 versus 3, 90 degrees being close, that means that this one is more favorable. Okay? So that's why we don't ever put our lone pairs, for trigonal bipyramidal specifically, we don't put our lone pairs on the axial, on the axis. It always goes on the equatorial plane. Okay? Why is it called seesaw? If I just rotate the sulfur so my equatorial plane is actually here, then you can see it's going to basically, here's my little pivot, and I'll just seesaw back and forth. So this is a seesaw. Okay, so when we talk about having 5 or 6 electron groups, then we're looking at trigonal bipyramidal or octahedral. So let's do an octahedral before I move on. And also, just before we go, I have a polar bond here, polar bond there, polar bond here, and polar bond there. So these might cancel each other out, but look at, nothing is canceling out the pull in this direction. So this is a polar molecule, and from the drawing that we have, it's going to be in that direction, towards the fluorines. Okay, on the equatorial plane. Okay, all right, let's give one more as an octahedral. Okay, so let's do xenon tetrafluoride. Okay, I have 8 plus 4 times 7. It's 36 electrons to work with. We're going to put in our xenon in the middle, surrounded by fluorines. Put in our octet. That's 32. I have 4 more electrons, so it goes on the central atom. Okay, I have 1, 2, 3, 4, 5, 6. I have 6 electron groups. So we know that our electron group geometry is going to be octahedral. I have 2 lone pairs. So the molecular geometry is square planar. So what does this look like? So octahedral has your xenon in the center. I have 1, 2, 3, 4, 5, 6. Okay? Now, put in your fluorines. And there are 2 options. You have your lone pair here, lone pair there. They're opposite from each other. Yes, they are interacting with the fluorines, but what other option do we have? Well, it's this one, or the other option is putting my lone pairs here. So, the problem is this. These lone pairs are 90 degrees from each other. I can't help all the interactions with the fluorines. They're just too close. These lone pairs are 180 degrees from each other. Oops. So this is more favorable. So because of the symmetry of octahedral, that if you have two lone pair electrons, you're going to have them as far apart from each other. So you're going to have them opposite of each other. So this is called square planar because it's on a plane and it forms a square. Is this polar or nonpolar? Well, this polar bond is canceled by that one. This polar bond is canceled by that one. So this is a non-polar molecule. And notice one other thing. I haven't talked to you at all about doing any resonance forms with these. And that's because all of these, I don't have any multiple bonds. They're all single bonds. How can I move electrons in a single bond? I would break a bond. And that's not what doing resonance forms is about. Okay, so let's do one last example. Okay, remember that once we draw a structure, think of all the different types of assessments we need to do, all the pieces of information that we can get out of a single drawing. So the last one we're going to do, we'll have multiple central atoms. Okay, so I'm going to give you something like a C3H6O. And we'll have a number of structures we can do. And I'll just do 2. Okay? So one of the things when you see this is these are all row 2. I'm not including hydrogen. So let's just say that my carbon and my oxygen. So we can only do an octet, no expansion. And what we're going to try to do is make sure we can do our octets, okay? So try not to go under. So let's do what we normally do when we say, oh, let's put all my least electronegative atoms in the center. Okay? And then, oh, let's surround it by an oxygen there. All right? So then let's draw our single bonds. Remember, I have 3 times 4 plus 6 plus 6. That gives me, what, 12 plus 24 electrons. Okay, so 2, 4, 6. Now, 1, 2, 3, 4, 5, 6. 2, 4, 6, 8, 10, 12. So I need to figure out what to do with the other ones. So I surrounded this by an oxygen. Now I need to put in my hydrogen. So let's just go ahead and say 1, 2, 3, 4, 5, 6. Okay? So let's see how many electrons I use up. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. Say, oh, I got to put my other 2 electrons here. Okay, well, that looks a little odd, doesn't it? Let's see. Why does it look odd? Because 1, 2, 3, 4, 5, 6. The reason it looks odd is this carbon has 2, 4, 6 electrons. This is missing an octet. And if we say, oh, let's just form a multiple bond, how are we going to share it? Because if I move it down and share here, okay, then the problem is I have an excess hydrogen. So let's go through, and remember we say the hydrogens for last, so they're the easiest to manipulate. So let's go ahead and say, I'm going to take this hydrogen out. Okay? And I say, all right, if I try to do the double bond, I've got to get rid of something. So I'll get rid of the hydrogen. I'll put the double bond right here. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. I need 2 more electrons and I need a hydrogen. So I'll put it right here. Now, every single carbon has an octet. My oxygen has an octet. My hydrogens all have a bond to each other. What's another way we can do it? So let's say, all right, instead of this, suppose I said something like, well, let's put 2 and 2, 4, 6, right? 2, 4, 6, 8, 10, 12, 14, 16, 18, right? I wanted to just distribute, okay, 22, 24. And let's distribute my hydrogens. So I can put a hydrogen here, 1, a hydrogen here, 2, a hydrogen here, 3, a hydrogen here, 4, a hydrogen here, 5. Okay, I need another hydrogen, a hydrogen here. You say, wait a second. Not an octet, not an octet. So why don't I take this hydrogen and put the octet on this carbon? Now I have octet, 1, 2, 3, 4, 5, 6, octet, octet, none here, 2, 4, 6, 8, 10, 12, 14, 16, 18, 22, 24. Okay. What happens if I share? I'm missing something. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. There we go. What happens if I share that lone pair here? Now you have that structure. Okay. So the rules that we told you about how to look at your central atom, they work up to a certain degree. But once we start getting to multiple central atoms, then bear in mind you're going to be playing with it quite a bit in order to try to satisfy your octet. Okay, that's really important. So the octet rule is essential when we do our Lewis dot, but we see that more when we do the multiple central atoms. In this case, because these are considered nonpolar, but this is a polar bond, so your molecule here is polar. Just like here, your molecule over here, it's polar bond here, polar bond there, so your molecule here is polar. Okay, so let's stop here and work on our next topic.